So in this video, we're going to talk about how to compute the moment of a force about an axis versus a point. So just like everything in your book, it talks about a scalar approach and a vector approach. And oftentimes you're like, why would they even talk about the scalar approach? It's a little bit confusing. But say, hopefully all of you haven't been in this situation recently, but you're trying to loosen the lug nuts on your tire. We all have familiar with using a lug nut wrench. We know that the longer this dimension here is, the easier it will be to use. And if you notice, the reason that this dimension of the actual wrench matters is that is a perpendicular distance from the point of application of the force to the actual axis, which is running perpendicular to the head of that lug nut. So in this case, what really matters with respect to loosening that lug nut is how much of a moment a force can induce about an axis that's actually perpendicular to the head. So you can use an actual what I would refer to as a scalar approach, as is described in your book. However, it's going to be always easier if you can just use a vector approach to address the problem. And the way that you compute a moment about an axis is just like the way you compute a moment about a point. You take the axis of interest and you pick any point, ideally the easiest one that will form a position vector that'll make your cross product easy, and then you compute the moment about that point. So just so no one is confused, when you think about it, when you were computing the moment about a point, that position vector had to start at that point, and it could go anywhere along the line of action of that force. When you're computing the moment about an axis instead, you now can pick any point along that axis to basically be your reference point. So you have another degree of freedom. If you're computing the moment of a force about an axis, pick any point on the axis to start at, and then draw your position vector to any point along the line of action of the force. And then once you actually compute that moment, in order to get the moment about the axis, all that you're going to do is to take a dot product of that vector moment, which you computed, with a unit vector along the axis of interest. And that seems really, really confusing. And the book tries to make it even more confusing by talking about this triple product that says when you take the dot product of a unit vector with a cross product, you can actually write it more simply in this form. However, I'm not going to ask you anything about the triple product. You can kind of convince yourself that this is the same thing as just taking a cross product and then taking a dot product with a unit vector. So let's actually look at an example problem. Here we have a force that's being applied. The direction of that force is specified by coordinate direction angles. We know its magnitude. And what we want to do is compute the moment of the force about the x-axis using the vector approach that we talked about in this module. So if you think about it, the way that we said that we would compute the moment of a force about the x-axis is pick any point along the x-axis we want, compute the moment of the force about that point, and then take a dot product with the unit vector along the x-axis, which we know that's just I hat. So let's think about how we would actually do this problem. So the first thing I need to do is pick a point along the x-axis. Well, it's probably pretty intuitive to you that the point you're going to pick is the origin, because you have to be able to write an expression for the position vector from that point to somewhere along the line of action of this force. Now, this is an example of what I was talking about a little bit earlier. In your textbook, oftentimes it's hard to see where another line of point along the line of action would be other than the point of application. And that's the case here. So to go from the origin to the point of application, I don't move any in x. However, in the y direction, I'm going to move in the positive 0.3 meters. And upwards from there, I'm going to move up 0.25 meters. So I'm going to start by writing an expression for the position vector from the origin to point A. It's going to have 0 x displacement. Along the y direction, it's going to have 0.3 meters of displacement. And along the z direction, it'll have 0.25. So I have that expression, which I'll show you in a minute here. Actually, let me show you right now, just so everyone sees. That's a position vector from O to A. And I picked this point because it's on the x-axis, and that's the point about which I want to compute my moment. Now I have to write an expression for my force. Well, if you notice, I'm given information in terms of the coordinate direction angles. The angular kind of displacement from the force to the x-axis is 120 degrees. From the force to the y-axis is 60. And from the force to the z-axis is 45. So I can write an expression for that force in Cartesian form is nothing more than magnitude 200. I will weight the x component by cos 120, the y component by cos 60, and the z component by cos 45. So just showing you what I have for that. That's how that looks. So the next thing I need to do is compute the moment about that point O, and it's going to be r from O to A cross with f. And that's just going to be using my 3x3 vector determinant for computing the cross product. And then let me actually open up a calculator here. I'm actually going to store this in my calculator. So I would say F is 200 times, sorry, this is some other research I was doing a little bit earlier. So the x component of the vector is the cosine of 120. The y component of the vector is cos 60, and the z component of the vector is cos 45. So those are the actual, and I'll write them in here, even though I'm not going to compute the cross product by hand. I'm going to show you how to do it in MATLAB instead. But if you choose to do it by hand, that's the actual matrix that you need to work with here. However, if you have a calculator that's capable of doing cross products, just define your position vector as well. So it's 0, 0.3, and 0.25. And then all you want to do is cross ROA with F, and you will get that answer. Let's actually talk about, we've spoken of this before, but I'm going to go ahead and round this to 3 sig figs originally, since I'm just taking a dot product after I get this result. But what will its units be? Well, it's still a product, right? It's a vector product, but it's still a product. And it was units of meters times units of newtons. So this is going to be in Newton meters. Remember, whenever you measure torque, that's the conventional units is a unit of force times a unit of distance. So this is MO. So that's step one was writing the necessary position vector and force vector. 2 was computing the cross product. And 3rd, we'll compute the moment about the x-axis by simply taking a unit vector along the x-axis, which is just I hat, and taking the dot product with that vector. And remember, when you take the dot product with I hat, that's just going to give you the x component. So this answer will just be 17.4 Newton meters. So hopefully that was pretty straightforward to everyone. And if you wonder, like if you skipped a video and you're like, why didn't you compute the cross product? We've done a few up until now. So just to make this a little more shorter and consumable, I'm going to leave that to you on your own, just based upon the examples that we've done so far.